Okay, so once again, work is how you put energy into and out of a system. We talk about work is equal to force times distance, either mass. And this is the example of where we would have needed the mg times d, because they give us the mass and not there. Because they are doing the same mass and the same over the same distance, the work is the same, but the time is different. And so here, which one is the rate at which work is done? The one that does the work the fastest will have the highest amount of power. So power is equal to work divided by time. Capital P, we're going with the units here. Capital P is power. One of the few variables or symbols in physics that actually make sense for what they are, especially as you go on, especially when you get into electricity. Power is measured in, what's the unit for power? Watts are the unit for power? Ha ha ha. Okay, never mind. Don't worry, I'll be here all week. Watt. The watt is the unit for power. It's no longer on this version of the test, but the test used to have a question that said, this is the unit for power. Who, what, when, where, why? Nobody got that answer wrong. So drive it up the averages with that question. So here's the confusing part sometimes. The unit for power is watt, which is usually commonly written as capital W. So the unit for power is capital W, but the symbol for work is capital W. So you have work, and just a reminder that this is written in joule, as a joule, or capital J. And of course time is in seconds. So if we're comparing the amount of power that's being used, we're not given numbers here, but the fact that the motor on the left did the same amount of work as the one on the right, but did it faster, that's the amount of power. That's why companies that try to sell you engines or motors are bragging about how much power they can do, how many watts, how many horsepower, because they're not just saying, okay, our competitor can do the exact same task as we have, but what makes us better? They can do the same exact task. They can pull the same load that we can pull, but what makes our product better? We can do it faster, yeah. So when you're buying a bigger and better engine, you're doing the same amount of work as something else, but you're doing it faster. If you think about it, that in terms of cars, if you have like a, I'm just using a Honda Civic because this is like a very generic, there's a lot of cars out there. So the amount of work that it can do, let's say to drive, a quarter mile, versus something like a dragster, which has the amount of work to drive a quarter mile is the same for each, let's say each car, but the fact that a dragster can do it in mere seconds means that it can put out that amount of work very fast. I was watching something yesterday where they were talking about dragsters, like I think it's like $3,000 for every second that the engine is on. That's how much it costs, and that's assuming that the engine doesn't just blow up. I think it says in 1 second, I think it guzzled, I think it was 20 gallons of fuel in a dragster. It's just like, so yeah, you get like, I think they worked it out, it's like 40 gallon, or it's a quarter mile per gallon or something like that in efficiency. So not as bad as my Mercury. My Mercury got about 16 to 18, miles per gallon. So this one gets maybe a quarter mile, which is just insane, the amount of energy. That's why, is it in Claremont? Is that where the drag strip is? That's why you can be miles away from it and just randomly hear them, because they're so loud, because they're doing the work to drive a quarter mile in a very short amount of time. Okay, anyway, so let's bring up what we were talking about up here with work into power, because when we're having our power equations, yes, it's equal to work divided by time, but it's not always going to say, like, here's 1,000 joules done in 1 second. It could also be giving us the amount of force being applied over some distance in a certain amount of time. Or, if they give us the mass, the reason I'm putting this in there is m times g is the force of gravity times distance divided by time. So we'll need to see which one of these are we going to use, which is why the equation sheet, or when we have our test, has all three of these here. Some other information about power. Up here. Should make it consistent across the board. Yep. Is when I think about power in work, it always takes me back to my football playing days, just because of sports. Now, for an offensive lineman, which I was, let's say I'm trying to push somebody 5 yards down the line. If I'm going to win, basically, in order for the play to take place, yes, I have to push somebody a certain distance. I have to apply a force a certain distance, but we're not going to do very well. We're not going to do very well in the game if I'm just saying, you know what, I need to push this person 5 yards, but I can take my time. I'll say like 20 seconds to do that, because by the time it gets the person to the 5 yards, the play's been over for 10 seconds. So, anybody have any words maybe in sports that your coach or coaches have told you in terms of how you can be powerful? You need to be this. You need to do your job. You need to do your task very fast. Yep. Okay, quick swing.
Drive.
What do you mean?
Drive your body.
Drive your body, yep. What? Explosive, yeah. That's usually, they're always like, well, I want you to be explosive. And you're saying what that means, like, I want you to do your job, okay? When you're lifting, when you're doing maybe bench press, it's not that I just want you to extend it there. I want you to do it as fast as you can. What about even in terms of running when you're coming off the blocks? Okay, it's not just about coming off the blocks and then taking your time getting going. The quicker you can get to your max speed, the longer you can be able to try to sustain that. So the term explosive is usually what I hear, and also let's think about what a watt is defined as well. Watt is equal to 1 joule per second. The unofficial. Down here. The unofficial unit, meaning the non-SI unit, for power is the horsepower. Now, where this term came from marketing. Selling the first type of engines that were sold, basically that, went towards the Industrial Revolution to grow that. There is a definition here that was later defined that one horsepower is defined as 746 watts. But where the term horsepower came from James Watt. I find those names interesting, where it's almost like like a TV show or a movie, where everybody just has regular sort of names, and then they're like who's that young gentleman over there? Oh, that's James Watt, and you see him working with you're like, oh my God, it's the guy that it's named after, because there's nobody named like Henry Horsepower, something like that, or they're like, hey, they're like they said that name, or a long time ago, we see this person working on an early form of a battery. What's his name? Oh, it's Alessandro Volta. And you're like, oh, does that relate to that? Or there's James Ampere. All these different people where their last names end up going in to be made to units. So James Watt, not the inventor of the steam engine, but the modern one, I would say. I don't like to necessarily, kind of carry around misconceptions. When I say modern, I mean like 1700s, 1800s, like what we think of a steam engine. And although he was he was a genius engineer, he was an even better marketer, because he realized I have people that I'm trying to sell the product to. They have absolutely no idea anything about mechanics, probably nothing to do with mathematics. Some of them may not even read. So how can I sell my device? If I have a secret device, or not secret, if I have a device and I'm trying to convince you of how powerful it is or how much work it can do, it would almost be like I have this new, this is actually what cell phone companies do nowadays. When they release, let's say, a new product, let's say on the iPhone, they always compare it to what? Maybe the last one, or the competitor. Because if they say hey, this is equal to some, if they say it's equal to some unit that you have no idea about, it's not going to be a good selling point. So he needed to pick some unit of power that would relate to what they were relating to. So here's actually, you may be thinking, okay, it's just the farm. But even in early cities that were being built here, you had multiple floors that were being used for production. And you would have horses. There we go. There's a horse. It's better than my other horses. You basically would have horses that would be traveling around in a circle, and just like they would be on a farm, and they're operating these mechanisms that are I've seen this where you would have this like spinning around, and the power would sort of be used from the central axis. The problem is with horses that you have to feed them, you have to take care of them, you have to transport, you have to find places to store them, or so that they can stay. And so here comes along James Watt saying, like, I have this steam engine, and I'm trying to convince them that this is powerful. How do I say it? And he says that, okay, if you buy this steam engine, it is equivalent to 3 horses. Now, a little bit of trickery, because if you're thinking the equivalent of power of 3 horses, you may be thinking of like the Kentucky Derby. Like, you release that horse and it runs for 10 seconds, and that's a whole lot of energy. It's going really fast. But were these workhorses that type of workhorses? Did they expend energy very, very fast? Or what do you think workhorses did? Did they work for a minute and then they were done for the day? No. They were instead, they could do a lot of energy, but they worked over a long period of time. So long story short here, he developed the horsepower. It is not equivalent to an actual horse's power. Oh, that's right there. I've seen this, I think, before in a book where they showed like how he defined a horsepower was like a horse lifting like 100 kilograms, 10 meters, and like 10 seconds. So like, it's not really that much. So he kind of fudged a little bit on what that meant, but that's why we still have that. Let's do an example from the book. We'll be calculating work and power, and I'll get that to you in a second here, Shelby. And it was the Empire. Here's the book. I'll go ahead and read it. A record for running up the stairs of the Empire State Building was set on February 3rd, 2003. The runner completed the 86 flights or floors with a total of 1,576 steps. You can imagine that there's like these back and forth all the way back, because you have nothing better to do until you got all the way to the top. 1,576 steps. Done in a time of 9 minutes 33 seconds. And each of the steps were 0.20 meters, and the mass of the runner was 70 kilograms. What they're asking us to find is, first of all, how much work is done, or I guess what is the amount of power output in watts that the runner had to have in order to do this many steps in this amount of time with this mass. And it brings us to, okay, we're trying to find what the power is, but which equation are we using? Are we using that? Oops. They don't just straight off tell us the amount of work that's being done. Are we using this? We can figure out the distance, but they don't tell us the force. They don't tell us the weight of the individual. They tell us the mass. So we need to figure out what is basically the force of gravity. So this is going to be our equation that we have here. So how do we figure out this distance here? Is it just 0.2 meters? Hopefully not. If it takes you 9 minutes and 33 seconds to raise your foot and lift yourself 20 centimeters, you're having a bad day. So how do we figure out what this actually is here?
You gotta multiply them.
Yep. Got to multiply them here. Got to multiply them. I have a hard time believing that this record hasn't been broken. I remember this from a college book when I was like in high school or college, sorry, physics book. So 1576 times 0.2, 315.2 meters. So that's the distance. Meters, it's like 1,000 feet. 9 minutes, 33 seconds. We cannot use 9 minutes. Minutes are not SI units. So minutes, how many seconds in 9 minutes? 540. 9 times 60, 540. Plus 33 is 573. That's in kilograms, so that's good to go. I want to actually, when we calculate this, figure out how much work is done. Because when we calculate the work is done, that's how much energy we need to just go up the Empire State Building, regardless of how fast we do it. Whether we take hours or whatever it takes, or how much energy it takes to lift somebody up that high. There. So.
Is that back down? Is it up and down?
What do you mean? It's just up. They just up. Yeah. I mean, you could be like, oh, I could do that. You maybe get through the first. I don't know. It says the average, so I wonder if he like really paced himself, or he just went as fast as he could for the first, something, because that's 86 stories. Crazy. Okay, so the mass is 70. Gravity 9.1. Distance we calculate is 315.2. One other thing I want to think about here is that would it matter if the stairs were traditional stairs or if they were just like a big ramp that went up like this? Similar to the problem that we did where it didn't matter the shape it doesn't actually matter how he would do this. He could actually climb a ladder, and if he was climbing a ladder this distance and this time with this mass, it would be the same amount of work. So what are the advantages of stairs compared to, I guess, a ladder? Yeah, I guess there's railings. And in terms of if you're going straight up, I guess another way of thinking of this is that the 315 meters, yes, you're going up, but by going sideways, by going upstairs, you're kind of making it. Yeah, you're a little bit. You're kind of. We haven't talked about mechanical advantages, but it's the difference between sort of if you have to get up to a certain height here, having a ramp that's really, really long and shallow versus having a ramp here that is that. Which one is going to be easier to go up? This one or this one? Which one? Let's say we have the same speed. This one is going to be easier to get up, but this one is going to have to take a longer amount of time. Where this one is going to be harder to get up, but it's going to be a shorter amount of time or a shorter amount of distance. So we'll bring that up a little bit later. And the time we had was 573 seconds. So the calculation on the top, 70 times 9.1 times 315.2, 216,447.84 joules. I feel like there's a problem in your book. I was reading it earlier, where you have to calculate how many candy bars he would have to eat. Let's say how many Snickers bars he would have to eat in order to get this amount of energy into his body to do this. That's why runners and sprinters, they preload with carbs or sugar so they have the energy to expend there. Divided by 573. So this top number here is how much energy it takes, no matter if it takes you days, months, years, seconds. That's how much the energy, it's the minimum energy. Now to figure out the amount of power we have, I think it's 377. We'll say 0.74 watts. Now, we're not typically comfortable always using watts. I guess, in what scenario are you probably most familiar on your day-to-day to come across watts? What did you say? Light bulb. So this amount of power is equivalent. Let's say we have a 60-watt light bulb. That's equivalent to about 6 light bulbs. 6. So if he could transfer his energy completely into those light bulbs, he would be able to operate 6 60-watt light bulbs for 9 minutes and 33 seconds. Let's go ahead and figure out how much power this is in horsepower. And the easiest way to figure that out is to figure out 1 horsepower is equal to 746 watts. So how many horsepower are equal to 377? And it comes out, if you were to do this, to be equivalent to about 0.51 horsepower. So not a lot. Matches up with what the book says. It says, let's see here. It says a leisurely stroll up the stairs requires about 1/6 of horsepower. For comparison, the power produced by a sprinter bolting out of the starting blocks is about 1 horsepower. And the greatest power most people can produce for a sustained period of time is roughly 1/2 horsepower. So we can see it sustain here. We'll look more of those a little later here. Last thing, let's talk about money in terms of bills. Paying those bills. Paying bills. There is something known as a kilowatt hour. You are going to be a consumer eventually, meaning that you are going to consume and have to pay. A kilowatt hour is how the energy or the power company charges you. So what is a kilowatt hour? You see the watt in there and you're thinking, oh, they're charging me based on the power. They're charging me on how fast I'm using it. But if you look here, so if power is equal to work divided by time, then work is equal to power times time. A kilowatt is how many watts? Kilo. 1,000, yep. 1,000. And an hour in seconds is 3,600 seconds. So a 1 kilowatt hour is 3,600. 1, 2, 3. It is 3,600,000 joules. Does anybody have any idea of how much that costs to charge you 1 kilowatt hour? This seems like an enormous amount of energy here, but surprisingly, Indiana, the amount it costs for one is anywhere, the highest I've seen, is about 12 cents per kilowatt hour, which is just crazy, because if you lift something that weighs 1 Newton, 1 meter, that's 1 joule. So it goes to show in some of our energy sources that we have, even the ones that are not as popular like coal and natural gas, that they give out so much energy and they're not very expensive compared to that. You could figure out how much your energy bill is. Let's say that you're living the minimalistic life and all you have is your smartphone. Okay, that's all you have. You could look up how many watts your phone is. Let's say when it's not on like power save mode or anything like that, it's on maximum power, and then you would just calculate how many hours per month are you using that. You take the amount of watts you're using times the amount of hours, multiply it, and then you can calculate what your power bill would be there. So your phone is actually really efficient. It's more like things that heat up. Some type of light bulbs are not really efficient, but where your home is spending probably the most amount of energy, what's causing you the most? What would you think? What stuff in your house is using up the most amount of energy? Chargers, but chargers actually aren't necessarily that much. What? Heat. Yes, heat is a big one. Heat is a big one. Really anything that controls heat, whether it be a refrigerator, which reduces the heat, or your actual heater. TVs are actually pretty high efficient because they don't release heat, especially ones that are like LEDs, because LED lights don't give off heat like incandescent light bulbs. So we might do that when we get to electricity. we'll talk more about watts, because watts are usually in referring to electrical outlets. And just real quick to show you, if you had a 60 watt light bulb and you had a 120 watt light bulb, how would you know, other than the actual printing, how would you know you're looking at a 120 watt light bulb? It's giving out more energy per second, and what form of energy is that? It's going to be brighter. So okay. And that basically wraps up what we're talking about right now. Tomorrow we're going to have a worksheet that has just various different things we're calculating. Like, hey, what is the work? But it's I would say multiple kind of really quick calculations rather than the full energy transformation one.